We are now looking at the gradation in property of alkali metals. So when we talk of gradation in property for any group, there are two aspects. One is there is similarity in property, and the other is gradation in property. Similarity in property is always because of similar outer electronic configuration. An example we can use over here is valency, combined capacity. All alkali metals have only one electron in the outermost shell. So all of them show a valency of what? They can either give one electron or share one electron in case it's a covalent compound. Just clear? So that was an example of what you call similarity property. But now we are talking about gradation in property of alkali metals. Gradation in property is associated with what? Change in atomic size. So gradation is because of increase in atomic size. Is because of increase in atomic size from lithium to francium. And increase in atomic size is because of increase in atomic number. So number of electrons increases. So number of shells increase to accommodate the increased electron. So let us look at it one by one. So as we can see, first we're talking about is ionization enthalpy. What happens in ionization enthalpy is, it is basically the energy required to remove the most loosely bounded electron. As you can see, this is dependent on what? It is dependent on atomic size. So as atomic size increases, what is happening? The energy required to remove the outermost electron decreases. Then gradation, pure gradation in property, where it decreases because francium would be more, ionization potential is associated with metallic property. So francium would be the most metallic among the alkali metals. Is clear? Because it can lose its electron very easily. Then we come to hydration energy. Now hydration energy decreases as we go down the road. But you can see over here I have written with a red pen, lithium. Lithium has this is considered to be a very high hydration energy. So what does this high hydration energy affect? So lithium is the strongest reducing agent. Lithium is the strongest reducing agent. So this is one reason. There are two reasons we are coming over here also. One of the reasons why lithium is a strong reducing agent is it has a very high hydration energy. Then when we come to melting point decreases as we go down the tube. And you can see over here, this is nearly 302 and 308. It's about 29 and 27 or 27, just clear degrees centigrade. So when from the beginning when I started this chapter, I told you that these are two examples of what? Liquid metal. They are liquid at room temperature. So out of that, which are the other two liquid metals we should know? Which are the liquid metals? You have cesium, francium. Mercury is something which you all are aware of, and gallium. So gallium will come in another group. Then we have got what? The standard reduction potential. The standard reduction potential, when you are arranging, standard means when it is for concentration 1 molar, okay? And when you arrange in the decreasing order, more the negative it is, more is the, less is the reduction potential. So it will be a strong reducing agent, okay? So, in fact, lithium is the one which has the least standard reduction potential. So minus 3.4, it has the least standard reduction potential among metals. Okay. So it will be a strong reducing agent. Least reducing agent means least reduction potential means it will lose electron very easily, undergo oxidation. So it will be a strongest reducing agent. Strongest reducing agent. So while we are on this, I'll give you a small tidbit that if this has the least reduction potential, which will have the highest reduction potential will be fluorine. Remember that. These are two extremes which you are supposed to know as far as entrance exam is concerned. So from this chapter, these are some points which can be what you call easily converted into a multiple choice question. We now talk about chemical properties. In the chemical property, we first talk about flame test. This is something which is related to the practicals that you do in your 11th and 12th standard. See, alkali metals and some alkaline earth metals, when you take their salt, their chloride salt, their salt in HCl, and keep it in a Bunsen flame, okay, it gives a characteristic color. That is one method of identification of what you call alkali metals. So lithium gives a red color. Sodium gives golden yellow color. Potassium is violet. Sometimes it's also said to be lilac. Lilac color. Rubidium will be red violet. And cesium will be blue in color. So these are characteristics of what you call alkali metals, and this becomes one what you call method of identification of the cation present in a salt in qualitative analysis. Then we come to formation of oxide. Very interesting. Formation of oxide. Now, in terms of formation of oxide, what happens? Lithium. Lithium forms only monoxide. Means others also form monoxide. Lithium forms monoxide only. Whereas what happens? Sodium forms monoxide and it forms peroxide. Na2O, sodium peroxide. Then you have lithium, sodium, you have potassium, rubidium, and cesium. They form monoxide, they form peroxide, and most important, they form superoxide. For example, you have KO2. KO2 is superoxide. Now, superoxides are paramagnetic. The next reaction is reaction with water. All of them, first point is what? All alkali metals react with water. So the reactivity of alkali metals with water is what? It is lithium less than sodium, less than potassium, less than rubidium, less than cesium. Now what happens is, when they react with water, lithium does not react vigorously. Lithium does not react Lithium does not react vigorously with water. Why? Because of high polarizing power. Because of high polarizing power. And it's very high negative standard reduction or low, and it's very low negative standard reduction potential. Of course, what happens is when they react with water, the others react very explosively with water. Others react explosively with water. To form corresponding hydroxide. And liberate hydrogen gas. Now, when we talk of the hydroxide that is formed, what is the property of the hydroxide? They're basic in nature. So, the decreasing order of decreasing order of basicity of hydroxide is, or I would say, we would rather put it like this. We would, why say decreasing? We'll start increasing because then lithium comes first. So we have increasing order of basicity of hydroxide of alkali metal. So we have lithium hydroxide less than sodium hydroxide less than potassium hydroxide, rubidium hydroxide less than cesium hydroxide. So basicity of the hydroxide increases as we go down the group. Is this clear? So what else increases for the hydroxide as we go down the group? Ionic character. So I'll write over here. In continuation of this, we can write for hydroxides of alkali metal. For hydroxide of alkali metal, what all increases? First is we have ionic character. So lithium hydroxide has more covalent character, less soluble because of high polarizing power. Then we have melting point. The third one that we have is we have boiling point, reactivity. So melting point, I'm right over here. Melting point and boiling point. So let's combine it together. They increase as we go down. The melting and boiling point of hydroxides increase as we go down the group. Thermal stability and solubility. Thermal stability, and fourth one is solubility in water. So we can always expect an MCQ being framed like this, multiple choice being framed like this, that which is most soluble. So obviously lithium hydroxide will be less soluble as compared to, let us say, cesium hydroxide or rubidium hydroxide. So these statements can be easily converted into a multiple choice question as far as this topic is concerned. We now talk about reaction of these alkali metals towards hydrogen. All of them, all alkali metals, all alkali metals react with hydrogen. All alkali metals react with hydrogen to form their corresponding metal hydride. General formula of the metal hydride is MH. But if you look at the reactivity, okay, there are two aspects to that. When you look at the decreasing order of reactivity, as lithium reacts faster, lithium is greater than sodium, greater than potassium, greater than cesium. So why is this so? Why is lithium more reactive? Lithium is more reactive because it is least electropositive. Lithium is most reactive because it is least electropositive. It is least electropositive. Let me make it. Least electropositive. Now, this reactivity of lithium, lithium being highest and then decreasing, also affects the thermal stability. So, when you look at the thermal stability of the hydrides, so we have decreasing order of thermal stability of hydride we have lithium hydride greater than sodium hydride, greater than potassium hydride, greater than rubidium hydride, greater than cesium hydride. Now, one of the other reason why they are this thing is because the lattice energy. The lattice energy of the alkali metal hydrides decreases as we go down the group, and that causes decrease in stability. So, the stability of the thermal stability decrease is attributed to the decrease in this is due to decrease in lattice energy of the hydride energy of metal halide as we go down the group. So therefore, one more point that I can mention over here, the third point is that these metal hydrides are ionic in nature. Metal hydrides are ionic in nature. They are ionic in nature. We now talk about reactivity towards halogen. Halogens readily react with alkali metals. They readily react with alkali metals to form corresponding halides. to form corresponding halide. The reactivity of alkali metals towards halogen is reactivity of halogen towards alkali metal is towards alkali metal is given by lithium less than sodium less than potassium less than rubidium less than cesium. Now here when we talk of halides, lithium chloride is a covalent compound. Lithium chloride is a covalent compound, whereas sodium, potassium chloride, rubidium chloride, cesium chloride, they are ionic. They are ionic. Solubility. Lithium chloride being covalent. Lithium chloride being covalent is sparingly soluble in water. Is sparingly soluble in water. But it is soluble in organic solvents like alcohol. In organic solvent like alcohol, like the other alkali halides are soluble in water. Other alkali halides are soluble in water. In water. And solubility increases as we go down the road. And solubility of halide, of alkali halide. Solubility of alkali halide increases as we go down the road. So we will have solubility in water will be lithium chloride less than sodium chloride, less than potassium chloride, less than cesium. So this is the order of solubility of metal halides in water.